let's look at an even simpler circuit. Here we go. A resistor here and a capacitor here. That doesn't look like it's going to do anything, right? If you made that and just set it on a table, it wouldn't do anything. Well, it might do something. It might be a useful way to look at discharging the capacitor. If in the last circuit we charged it, this might be a way to discharge it. So let's analyze that, but the key is we're going to use Kirchhoff's loop rule, and when you do that, don't think about what's going to happen in the circuit. Don't think to the end. Just apply Kirchhoff's loop rule. And one of the first things you do is you say the current is going to go that way, and I'm going to loop clockwise. That's all you got to do. Okay, loop rule. I'm a little test charge. Okay, and you're going to go across this capacitor. Well, if the current is this way, it's going to build up positive there and negative there. So we're going from high to low. So that would be minus Q over C is the potential drop across capacitor. And now you're going again with the current across a resistor. So that's minus IR. And then you're back where you started, equals 0. That's what we get from the loop rule. So now it's similar to before. I'm going to solve this for I. I'm going to bring this over here, and I'm going to divide by the R. And I'm going to get I equals minus Q over RC. And we can't really do much with that because here we have Q and here we have current. But of course, the current through the resistor is the dQ dt on the capacitor. So I'll say dQ dt equals minus Q over RC. Well, we can't integrate that because we don't know Q, but we'll do this thing where we switch it all around, and this becomes dQ over Q equals minus dt over RC. Okay. And now is the time we have to think about what we're doing. We have to think about the physical experiment because now we're going to integrate. And we have to have limits on the integration, and those limits have to match what we're doing. So let's imagine then that we're starting with a charged capacitor. So it starts at Q naught, and it's going to change from Q naught to some other charge Q. Okay? So Q will become sort of our function, but Q naught is our initial value instead of 0 like before. That's going to happen. We're going to start at time equals 0. So we're going to say it has some charge Q naught at some time equals 0, and we're going to go to time t when it has some different Q at time t. All right, so let's do our integral. The integral of dQ over Q is just the natural log of Q evaluated from Q naught to Q, and the integral of minus dt over RC is minus t over RC evaluated from 0 to t. So this is the natural log of Q minus the natural log of Q naught, and when you subtract natural logs, it's a ratio. So this is the natural log of Q over Q naught, like we did just a minute ago for me, and this is still minus t over RC, because when you plug in 0, you get 0. All right, similar, exponentiate both sides, and this becomes Q over Q naught is e to the minus t over RC. All right, so then we solve that for Q, and then here is your Q as a function of time, the charge on the capacitor, and some initial value, e to the minus t over RC. So if we were to plot that, that's just exponential decay. So that's saying if we have this capacitor charged up, and we just start the circuit at time equals 0 or close the switch, say, the charge will go down. And that makes sense. If the charge is built up here, it'll flow, and this charge will flow over here to neutralize the capacitor, and it will eventually go to 0, and nothing will happen. Well, let's look at the current and see if that makes sense. The current is dQ dt. So that equals, that's just a constant, so e to the minus t over RC. The derivative will remain e to the minus t over RC, and you pull out the derivative of this part with respect to time, which is minus 1 over RC, minus Q naught over RC, e to the minus t over RC. And that is your decaying current. And look, a negative sign showed up. Because sure enough, if we have positive charge here built up on this capacitor, and that's our initial condition, then the current's going to go the other way. To set this up, I assumed the current went this way, and I assumed it was all like this. And I said, don't think about it. Just start setting it up for Kirchhoff's law rule. It's better not to think about it ahead of time. Just set it up. And in the end, it will work, because here we have an initial current that eventually goes to 0, but it's actually negative, as it should be. So if this is I, and here's negative current, it's negative going the opposite direction of how we drew it, and it decays to 0. So therefore, there are the circuits to both charge and discharge a capacitor.